everybody, for participating in our PorkBridge session today. Today, our speaker is Dr. Mike Brumm, who, after a successful year as Professor of Animal Science and Extension Swine Specialist at the University of Nebraska, incorporated Brumm Swine Consultancy in the summer of 2006. As an industry consultant, Dr. Brumm spends about 50% of his time as Science Director for 4 2,400-head wean-finish research barns. The remainder of his time is spent working with a variety of clients worldwide on housing and management issues. He spends much of his time in client production facilities investigating ventilation and housing issues. He's a frequent presenter at producer conferences on issues dealing with housing and management, with a special emphasis on feeders, drinkers, ventilation systems, and ventilation system controllers. In addition, he is a frequent contributor to industry publications. His most recent award was the 2013 Outstanding Pork Service Producer Outreach by the Nebraska Pork Producer Association. And with that, I will hand it over to Dr. Mike Brumm to present on Are You Smarter Than Your Barn Controller?
Well, thank you, Sarah. Some of you that may have dialed in early might have heard some of our conversation as we were setting up today's talk. This marks the 11th year of PorkBridge, an effort that I was involved in starting back in 2004 with a group of Nebraska and Ohio producers. So it's nice to see that we're still bringing value to the industry via this method of education. So turn to your screens and bring up the title slide, which should show me wearing a University of Nebraska sweater. Sweater is probably appropriate today. In southern Minnesota, it's 34 degrees, and they're talking 6 to 12 inches of snow tonight and tomorrow. So winter is still with us, and as such, all of the issues that you faced all winter and fought with maybe in your controllers is still with you. So let's go to the next slide. Slide number 2 shows a whole bunch of controllers. And regardless of which of these devices, and there's probably devices in barns of people participating today that I don't even show, regardless of whether it's a Vera Fan, a Faison, a Genus, a hired hand, Expert, TC5, whatever, all of these do the same thing. And what I'm going to try and help you with today is make you unafraid of your controller so that regardless of which controller you have, you can help it do the same thing. Slide 3. In my experiences, as I get in lots and lots of barns, I find all too many producers and employees in barns that are afraid of their controllers. I use the nice word intimidated in my slide here today. What I see in a lot of contract barns is the service people for a production system says, don't touch the controller, I'll take care of it. And while that's easy for you if you're the contract grower because you can say, I don't need to know, yes, you do need to know because someday you may have a different service person or things change and all of that. So just because they say don't touch doesn't mean don't understand. The second thing I see a lot of is you've got a controller and you really don't understand what it is you're trying to do. You know you're trying to create conditions for the pig, but you don't understand how the exact settings that you put in your controller influence how those conditions get arrived at. And for some of you, you got talked into a bill of goods. You have a controller that's got bells and whistles and everything else, and all you needed was something to turn fans on and off and make a curtain move. So all of that has compounded our industry challenge of intimidation and fear. Next slide, number 4. Today I'm going to spend the talk with the assumption that you Stage 1 in your controller is a variable speed fan. I'd say about 95% of all our Stage 1 fans in the industry now are variable speed. And some of you may have Stage 2 variable, some may have Stage 2 single speed, some may have Stage 2 make a curtain move even. But let's start with Stage 1 variable. In your controller, regardless of which brand model you have for controller, there's 2 settings you always have to make. One of the settings is minimum speed. How slow should the fan run when the temperature in the room is below the set point? And notice I've got something called motor curve in there that really is critical to this, and we'll get to it in a minute. The other thing you tell the controller is bandwidth. Faison calls it range, and that's how many degrees from when the fan first starts to speed up until it's at full speed. So if you have a 50% bandwidth, 50% minimum speed, and a 2-degree bandwidth, that means when the temperature is 1 degree above set point, the motor speed should be at 75%, and at 2 degrees, it's 100%. And we're going to give you recommendations on settings for both of these numbers as the day progresses. Slide number 5. So, a question for you. Some of you obviously have cheated and looked at the answer, but think about this one. We being the multi-state ventilation workshop group from Iowa, Nebraska, South Dakota, and Minnesota that I'm still part of even though I've retired from the university, we do an advanced ventilation workshop. And in that one we spend time on controllers, and we always ask this question. And the question is, when you set 50% minimum speed on your controller, or if you've got a Ventra or Ventra Pro, when you set 30 as the minimum speed, what are you setting? Are you setting the controller so that you get 50% of the rated fan CFM? Are you setting it so you get 50% RPM on the motor, which has a fan blade on it? Are you setting the controller to send 50% of the incoming line voltage out? Or is it a funny number? When we do the ventilation workshops with this question, we generally get all answers to all of them, hands raised for every one of them. And go to the next slide. In slide number 6, the correct answer is, it's a funny number. Until you specify more details about your controller, 50% minimum speed means nothing. Slide 7. So, to help us understand why 50% is a useless number until we have more knowledge, let's look at 5 variable speed fan rules that I've put together to help explain your Stage 1 ventilation. First rule, speed does not equal CFM. 50% RPM is not 50% CFM. Slide 8. This is a graph of the CFM versus RPM output of a 12-inch fan. And in general, every fan where I've got output known against RPM, you achieve 50% CFM, somewhere around 62 to 65% of the RPM of the fan. And the reason is you've got to turn a fan blade so fast before you can create the static pressure at the blade around the fan housing with the clearances of the blade, etc. So 50% CFM is about 62 to 65% RPM of a fan. Slide 8. Rule number 2, 50% voltage does not necessarily equal anything. Slide 10. Here's one example. This is a 24-inch fan we're looking at output from the best laboratory in the Ag Engineering Department at the University of Illinois, which is the fan rating service that we recommend everyone use as they try and understand their fan performance. So this 24-inch fan with a 230-volt incoming voltage when it's wired that way at 0.05 static pressure at full voltage gives us about 7,200 CFM. 0.05 static pressure at half voltage, 120 volts, we're 1,800 CFM. So voltage does not necessarily directly equate to CFM. Slide 11. And the reason for this is every motor reacts to voltage differently. It depends on the copper winding, the starter method, and lots of stuff that I don't understand. And generally, this, as fans get smaller in size, as we go from 24s to 18s to 16s to 12s to even some 8 and 10-inch duct fans, we really see variation in how these fans respond to the same incoming line voltage. Slide 12. So, best way I've found to explain this is we're going to look at 3 fans. These are 3 common fans that many of you listening have installed, either in farrowing houses, nurseries, for sure the 18s and 24s would be in finishers. So we've got an APP 12F fan, that's a 12-inch fan from AP, an 18-inch Aerotech, which is the brown, and then the blue line is the APP 24F. And we've expressed fan output on the left axis as a percent of their rated capacity. We don't care that the 12 is only 1,400 CFM. That's why we put it in to get that. So we're just saying 100% of it's rated. And we've expressed it versus voltage. So this is how the fans perform when they're wired for 230 volts. Next slide. If we were to send 50% voltage, 115 volts, to these fans, 2 of the fans, the 18 and the 24-inch fan, would give us about 20% of their rated CFM, while the 12-inch fan is going to give us 80% of the rated output of the fan. And all of these fans could be connected to the same controller. Next slide. So, if I want to get 50% CFM, which is ideally what you think you're setting in your controller when you set minimum speed, with the 12-inch fan, that fan would need an input of 107 volts when wired for 230. The 18-inch fan would need 132 volts, while the 24-inch fan needs 142 volts. So you can see that each of these fans responds differently to the same incoming line voltage. Slide 15. To help you better visualize all of this, let's look at the actual output of these fans as furnished to me by AP and Aerotech. This is the 12-inch fan. I've circled in red on each of the columns the approximate 50% value. So if I send a 50% voltage signal to the 12-inch fan, I'm going to get 80% of my CFM. If I send a signal of 104 volts, which is well under half voltage, to get 875 RPM, which is half RPM, I'm going to get about 35 to 40% of my CFM. And then, of course, I have to increase voltage and RPM to get 50% CFM. Slide 16. Here's that 18-inch fan. And you'll see a total different pattern of how the circles lay out. Half voltage on this one only gives me 20% CFM versus 80% before on the 12-inch. Half RPM, and I'm a little under half at 800, only gives me 30% CFM, and I've got to be well up to get 50% CFM. And finally, on slide 17, the APP 24F that I know a lot of you listening would have on your pit fans. Here's their pattern. Half voltage is 20%, half RPM is 40%, and then we have to increase again to get 50%. Slide 18 is you've many times been told not to set your controller less than 40% minimum speed, or in terms of setting. What they're really telling you is that when everything is correctly set in your controller's background setup, the minimum speed of 40% is actually 50% RPM. And you saw that roughly in the numbers I presented. And the reason for this, slide 19, is that fan motors are totally enclosed air over, and they need a minimum amount of air over the motor for cooling purposes. If we don't put enough air over the motor, we tend to increase the burnout of the motor. As producers, you're more than aware of that. Faison Controllers, which is Airstream, Aerotech, Acme, Radot CVS, Velco, Ovation, all those controllers, when we get something called motor curve, which we'll talk in just a minute, correct, we say never set it less than 40% minimum speed. With the Ventra Ventium, for those that might be using that, or the Ventra Pro, that one, there are no hard and fast recommendations because you have to know the individual motor that's attached and how it responds. I can say with the Velco 21-inch fan that many of you would be using as pit fans with the Ventra and Ventra Pro, 24%, because the Ventra full speed is 60. A setting of 24 will give you 50% RPM on your motor and is the same as a 40% setting in other controllers. The challenge we've got with variable speed fans, and we're all aware of this, is that as speed goes down, wind and other things that impact static pressure have a bigger response and impact. And what I commonly see in barns is, especially in cold winter, I need to turn my fans down. I only got half the pigs today, and it's going to be 3 days or 5 days before we finish filling the barn, and I don't want to burn propane, so I'm going to turn my fans down to 20%. If there's 2 fans on a stage, anytime you have to consistently run the stage less than about 45% minimum speed, I recommend you unplug one of the fans so that the existing fan can be ramped up. Now, if you have actuated inlets, you have to obviously be aware that the controller doesn't know you turned the fan off, and you'll have to turn inlets off or otherwise account for that. But next slide, slide 20, illustrates this very well. This is, again, data from the best laboratory at the University of Illinois, 24-inch AP fan that many of you also would be having as pit fans. So at 0.05 static pressure, full voltage, you get 5,800 RPM from the fan. You get 50%, not RPM, CFM. You get 50% of the rated capacity of the fan when you send 160 volts to the fan as a signal. Now, if I keep sending 160 volts, but I get a 10-mile-an-hour headwind directly into the face of that fan, static pressure will go up to about 0.1, and fan output falls to 20% of the rated. There's the impact of wind on variable speed fans. And as you can see, you go from the black line, which is the response function at full voltage to increasing pressure, to the red line, to the green line, to the purple line. As you lower voltage, as you slow the fan down, the drop-off due to pressure is more severe. That's why I say we always want to, if we can run one fan versus two, always run one at a higher speed so that wind has less impact. And again, the caution of actuated inlets needs to be out there. Slide 21. Finally, the last rule is we need to think of controllers as voltage machines. That's what they are. They're sending voltages to fans. On-off, it's real easy. They're just on-off switches. But on variable speed fans, they're sending a voltage signal. A reminder while I think of it, you cannot use a cheap voltmeter to read the voltage outputs on these controllers. Because they have potentiometers in them and doing the electronic manipulation of the circuit, if you actually wanted to pick off the voltages that were being sent, you'd need to use something called an RMS meter, root mean square meter. That's the only one that has any chance of being accurate when you're trying to read voltages on variable speed relays. Slide 22. So let's get down to specifics of controllers. Put names on them, turn knobs, and all of that. We're going to start with this series of controllers. These, whether it's Acme, Aerotech, Airstream, Radot, Velco, the Ovation, or the CVS from Radot, all of these were made by a company called Thevco, a suburb of Montreal. That is now owned by something called GSI Electronics, which is GSI, which is now AGCO, the orange tractor people, and everything else. But these controllers have been around for a long time, and whether you've got a blue faceplate like the Aerotech Ultra on the upper right, or it's the Expert, or it's the TC5, or the CVS 22, or whatever, basically they all internally do things very similar. Slide 23. So we're back to our three fans. We've got one of those controllers, and we're going to put one of these fans on stage one. How does that controller know what voltage to send and what's connected? Well, in these controllers, it's something called motor curves. Slide 24. And these controllers have 10 different user-selectable motor curves. And what they are is this is the internal workings of that controller. The voltages given here are the motor curves that are installed in the Airstream Expert as pulled off under laboratory conditions. Voltages in your controllers when installed on the farm might vary slightly because of incoming line voltage, could vary slightly depending on the date and model you were made, but they're going to be similar. So when your controller reads 50% minimum speed, if you have one of these controllers, you could be sending 92 volts to a fan if you had motor curve 10, or you could be sending 161 volts if you had it set for motor curve 5. And your controller reads 50% speed. Slide 25. Similarly, when your controller reads 90% speed, you could be sending 123 volts on motor curve 9 and 205 volts on 4 and 5. So what you've got with motor curves is the directions of how to send voltage as you ramp through the minimum speed. I've circled in red motor curves 3, 4, and 9 because these are the recommended curves for the 18-inch Aerotech, the 24-inch AP, or the 12-inch AP. And if you look in the upper right where I put the graph again of how those respond, you can see, get a visual idea of how these motor curves come closer to matching how the fan responds to voltage. Slide 26. Well, how do you know which motor curve? Well, when your controller was new, there was a goldenrod sheet like the one on the left somewhere with the owner's manual. And most chances are it's lost. It's gone. It's in a pile somewhere. It got burned. It blew away. I've heard every excuse I think there is. You now have the motor curve sheet. And what you do is, obviously, you look up your fan or your motor, and it tells you which motor curve to use in the controller to get the best response when used as a variable speed. On the right, I've put the 3 most common fan brands that I work with in terms of their recommended motor curves that get installed. The other one I do want to point out is the 21-inch Radot and the 24-inch Radot. I tend to see these installed with the Radot CVS controller in nurseries and using the wrong motor curves. They are clearly different also. So think of the motor curve as where you tell the controller, what is connected to it. Slide 27. Where do you find motor curves? Well, if you've got the Expert or the Ultra or the Acme controller, depending on the model, the new Expert Series 2, for example, it's right under each fan stage. Under the Expert VT110, the VT212s, those controllers, there you have to use the password and get in the installer. The controllers come with motor curve 4 as the default. If you've got the white boxes like these that I show here, you need to turn the left knob to bandwidth and then push the function button. If it's a newer controller with the rounded corners like a TC5 or the ST5222 Aerotech, you push it 3 times and the screen will say on, off, and then TYP. And then you turn the right knob to scroll through motor curves 1 to 10. Some of the older versions of this controller, including a TC4 from Airstream, the first time you push the function button, it'll come up with the number. And you'll turn the knob again to scroll through the motor curves. And I'm convinced that there's a gremlin that runs through hog barns that resets motor curves at 2 at night just to make us mad. Because I get in way too many barns where the guy says, I know I put the motor curve right, and we check it, and it's something that isn't anywhere close to what that fan requires. Next slide. What about Faison controllers? Because there's a lot of Faisons out there. It depends on which Faison and how old it is. Some of the Faison controllers, especially if you have the manual Faison variable speed controller where you set a minimum speed by turning a knob and then the fan goes faster as automatically. It could be an independently wired fan from a controller. That is a straight linear voltage output. And that's why small fans on these variable speed controllers, you barely move the knob and the fan goes from slow to fast. Go back and review the data on the 12-inch AP fan where movements of 2 volts gave you a 10 or 15% change in output of the fan. Slide 29. A lot of you have the PAC Plus. We'll tell you right now, if you have the PAC Plus and haven't upgraded software, your motor curves are wrong. This controller, as it originally came from the factory in Winnipeg, has 2 variable speed curves. In order to get your variable speed fans to have any chance of working right, you either have to set the minimum speed at about 22% or minimum speed at about 80 with most fans that get connected at all on them. Slide 30. The good news is Faison has recognized the error and has upgraded software. So I've circled it. If your controller is one of these products, and they list serial numbers and some more information I have from them, you need to get from them the software patch and upgrade the controller, slide 31. And now they have 4 motor curves that indeed have a chance of matching the fans and the motors out needs so that you get a better response. Slide 32. Faison Supra. I tend to see these in nurseries and in tunnel wean to finish barns. Faison Supra, we have many dealers, unfortunately, that want to install all of the fans on the optimum curve, the Faison curve. That's not right. The Supra comes with 5 other user-selectable curves. They're listed on page 154 of the owner's manual, and my experience is when we put the correct curve in the controller, the fans begin to function as we intend. Slide 33. What about Vera Fan? See a lot of Vera Fans or Montrol in Canada controllers. Generally, these are used in barns that have multi-fan fans, and they have 8 or 9 motor curves. I've circled one fan because this consistently is a problem that I see in barns, and that is nurseries especially that have the 18-inch 4E45 fan in a nursery, on a pit fan or stage 1 fan. Most Vera fans, multi-fan fans that we're putting in barns, require motor curve 2, but this one is 3. And I consistently see the wrong motor curve on this fan and can generally improve the ventilation system performance by, again, getting the correct motor curve into the controller. Slide 34, hired hand. Hired hand has 3 motor curves, fan 2, fan 1, fan 2, and fan 5 on this list of motor curves for single-phase 230 wiring. Generally not much of an issue as long as they're only using 34 or 24-inch fans for the variable. Have no experience with hired hand on smaller motors other than in some farrowing sites. And again, it was a matter of experimenting because they don't publish a list of which motor curve will give us a reasonable response. Slide 35. What about the Ventra or the Ventra Pro? We said they do not have motor curves. In the owner's manual is this statement that, yes, motors vary. For example, to get that 12-inch AP fan that we've been using in the examples to work right with a Ventra Pro controller, I have to have the on setting at 17, whereas 30 would be a 50%, and I have to show full power at 42 so that I can make the fan behave as a reasonable variable speed fan. The Valco 21-inch fans generally, as I said before, perform exactly as expected when connected to these controllers. Slide 36. So we've told you what some of the background of the differences in controllers. Now let's start setting controllers and putting it together. So basic settings in controllers. Stage 1 variable. I'm going to argue vehemently that stage 1 should always be a 2-degree bandwidth. You're at the bottom end of a thermal neutral because if it's colder than set point, stage 1 is going to be operating at minimum. So you've got an itty-bitty fan on a great big room. So give it some time to work by putting some bandwidth in. I've seen where people have said, I want things to be really tight in the room, so they set stage 1 at a half a degree bandwidth, go from minimum speed to maximum speed if the room warms half a degree. And the first time the pigs get up and become active in the barn, there's enough heat generated, it blows through stage 1, stage 2 comes on, and then it drops off, and then it comes on, and you end up with fan cycling a lot. 2 degree bandwidth on stage 1. And again, as we said before, never less than 50% RPM, which when the motor curve is correct, is a speed setting of never less than 40%. Stage 2, generally set that so that it comes on a half to 1 degree after stage 1 is at full speed. The reason for this is generally we want then, once the fan comes on, for the room to cool a half to 1 degree before it shuts off. But we want it shut off before it laps over on stage 2, on stage 1 again. So that's how I would set stages 1 and 2 in a controller. 37. Let's go to curtain barns. In curtain barns, the challenge we face is how to set the controller to operate the machine. Anymore, almost all curtain machines use the ventilation controller for the timing. The only one that I'm aware of that doesn't is the 18 Newell, the older 18 Newell, that has the self-timing clock mechanism on a set of gears in the controller, in the curtain machine. Otherwise, you set everything in the controller. And the basics of this are we move the curtain long enough to result in a 2 to 3 inch opening if the curtain has to open in cold weather. Generally, it would be a grow finish barn that only has 4 pit fans, and then we immediately go to the curtain and there's no wall fans. Generally, you're limited in fan capacity to somewhere around 20 to 22 CFM per pig space, which means it's cold when the curtain opens. So you don't want to move the curtain very far. Newer barns that are built today, a lot of them, they've got 4 pit fans and many times 4 24-inch wall fans or 2 36-inch wall fans for 1,000 to 1,200 head room. Well, now it's going to be a lot warmer when the curtain opens. So now we can move the curtain 4 inches at a time because it's warmer. The critical number, though, in curtain control is the off time. How long after the curtain moves should it set and not move before I call for it to move again? Generally, that needs to be 90 to 120 seconds. So a minute and a half to 2 minutes after a move before it moves again. The reason being is you have a series of temperature probes, 1, 2, or 3 probes, generally down the middle of a barn, and you've got curtains that are located 20 to 25 feet away from these probes. So you've got to give it time to influence the probe. If you've got a curtain that's constantly moving, up, 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 down, 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 up, down, down, up, generally that means you haven't let it set long enough to react to the change, so we have to increase the off setting in the controller. Slide 38. We said it's 34 degrees in Mankato today. Well, that means my furnaces are still running because we finished weaning pigs to fill a site today, and it's cold. So let's talk about furnace sizing, and then we'll put the furnaces in the controllers. See a lot of mistakes made with furnaces because we all buy big furnaces because they're a better buy, more BTUs for the money. But our target should be a furnace is big enough if it shuts off on the coldest day of the year. And in managing the furnace or furnaces in a room, we want furnaces to run a very long time because the longer the furnace runs per burn cycle, the more uniform the heat in the airspace that you're heating. Again, the longer it runs, the more uniform the heat distribution within the airspace. So we're going to manage furnaces to get long run times. Slide 39. Couple ways we do that. If you have LB White Guardian furnaces, PSI furnaces, or the new hired hand furnaces, they have a blue variable output valve. And I've showed it on 3 furnaces here on the picture. This valve varies the heat output of the furnace. In the lower left, the valve is parallel to the gas line, so you're getting full heat output. In the upper right, it's perpendicular to the line, so you're getting the lower heat output. For example, the LB White 250,000 furnace Guardian Series, if you turn the blue valve a full quarter turn, you get 170,000 BTUs. All hog barns in North America in September should have the blue valves turned to low, because you don't need a lot of heat output in September to warm a space. When do you turn them to high? Drum roll, please. When they don't shut off. Not some magical in January. And what I found on many people, again, depending on their fill sequences in their barns, you can get by leaving them on low year-round. The goal is a long run time. If they shut off, they're big enough. Slide 40. So, question becomes, how many furnaces do we need to put in a barn? And we need to remember that the cold air return on all of these furnaces, all the brands I indicated there, is always the underside of the furnace. So the coldest pen in the barn is always the pen under the furnace. If we can make furnace runtime longer, we stand a chance of getting more heat back to the pen under the furnace. So a typical layout of furnaces here in southern Minnesota and northern Iowa for 1,000 or 1,250 head room, especially wean to finish, is going to be 3 furnaces, usually in a layout like I depict in the white box. 2 different ways we can make this happen. If all of the furnaces are wired to a single stage in the controller, in late spring, early fall fills, such as late April through early mid-October fills, depending on where you're at in the year, I'll physically unplug the 2 outside furnaces so that only the center furnace runs. When the center furnace never shuts off, it's time to plug in the outside furnaces and now unplug the middle furnace. When the 2 outside furnaces can't keep up, you add the middle furnace. If you have more than 1 furnace circuit available in your controller, what we're doing there is setting the controllers so that one of the furnace stages is a half a degree lower or 1 degree lower than the other stage. So in spring, fall, we set the stage with the single middle furnace, so it's the warmer, runs a warmer temperature. The room gets 1 degree colder than that, then the other 2 come in to help. Slide 41. In general, on setting furnaces, we start with the off temperature in a furnace, and for those of you that have TC5 controllers, it's called the offset. The off temperature or offset should be 2 degrees below set point. Now this assumes that the variable speed fans begin to ramp at 0.1 above set point. Especially in the Ventra and Ventra Pro controller, the ramp temperature is independently selected when you set up the controller. So we say just the furnace should shut off 2 degrees below the temperature at which fans ramp, and then we'll adjust it accordingly. The on temperature should be 3 degrees below, or in the TC5 differential of 1. 3 degrees below. And I like a 1 degree range from on to off because it gives me a longer burn cycle on the furnace, more time for that furnace fan to influence the space. I see a lot of people like to set their furnace on-offs only a half a degree apart. It results in short run times on the furnace, and you don't get to use the furnace fan as an air distribution device. In cold weather, come next winter now when we start filling barns again, you can use your controller to know if you have your furnace on-off temperature set correctly. As a result of your furnace operating, your high temperatures should be a half degree approximately below the temperature at which the fan ramps up. So you should never get to set point as a result of furnace operation, because at 0.1 above set point in most controllers, fans speed up. And so you should never get to set point as a result of furnace operation. Slide 42. Well, a lot of you have brooders, especially in wean to finish. And this is where we do make lots of mistakes, as we've learned. So let's start with those of you that are using LB White brooders and have this control on the wall to run your brooders. What this is a high-low, so there's the pressure regulator on the bottom is a low-pressure regulator, generally set at about 1.2 to 1.4 psi of gas pressure. The high side goes to line pressure, usually 5 psi coming in, and you dial a temperature that at which the flame goes to high to low. Problem we see in many wean-to-finish barns with brooders is the brooders are on high and fans are ramping up to get rid of heat in the barn. And that makes no sense. Why do I have brooders on high adding heat if I'm getting rid of heat? Well, the reason is because we haven't changed our thought process. So when we're using brooders, the controller set point, the temperature at which fans begin to ramp up to remove heat, needs to be the temperature of the white knob, needs to be the temperature at which the flame goes to low. The room temperature should be set in the controller, so you change the furnace settings in the controller for a much lower temperature, because that's going to be what you want the room to be back away from the brooders. 75 to 80 degrees would be most common. So while the controllers are connected, you don't put the off temperature within 2 degrees of set point. You might make it 10 degrees lower than set point. This will help a lot in terms of saving on propane use. Now the challenge on all of this is where is the probe for the brooders? Slide 43. I see too much of this. The brooders are running. The probe is still got the thermocouple hanging on the wall just like this. These are not meant to be room heaters. The probes are meant to detect radiant output from the brooder, and they're connected back to the control valve to regulate the radiant temperature. Slide 44. The correct setting for the brooder probes, this is direct from LB White, says the probes need to be as close to the animals as they can be, somewhere 4 to 6, 8 feet away from the center of the brooder, sensing the heat output of the brooder. Slide 45. We'll end some of our discussion on controller and controller settings by looking at actuated inlets, because we're moving as an industry to now controlling inlets with our ventilation controllers. When we use actuated inlets, we're using one of 2 devices to operate the inlets. We're either using a ram, such as on the left, or a curtain machine, such as on the right. Slide 47. The challenge is that every controller, again, uses different language. And someone like me has to understand these languages. Your challenge is to understand the language of your controller so that your inlets run correctly. Slide 48. Biggest challenge we have in controllers anymore is that controllers can be run with seconds of runtime or with a feedback loop and a potentiometer in the controller that tells you where the inlet is. And we'll talk about that on the next slide. If you have a controller that's using seconds runtime, that is, move so many seconds when this fan comes on, they have to be recalibrated daily because over the 24-hour periods of movement, they get out of calibration. Originally, many people wanted to do this at night while pigs were sleeping. In fact, the best time to do it is late afternoon because of icing on inlets. Also, just if you're putting or looking at actuated inlets, get at least a double loop in a 2-to-1 ratioing in the curtain machine if you can, because it'll make for fewer errors in the movement, and get a hand crank on the sealing inlets. Slide 49. If you've got the Airstream Expert, and I don't know about the Aerotech Ultra, if you've got the Airstream Expert or the Ventra or Ventra Pro, and you currently use a potentiometer as the feedback mechanism for inlet location, both of these controllers now have new software available where you can convert the controller from potentiometer to seconds runtime. And the reason people are doing this is you get tired of something called pot defect error that flashes on the screen. And what this means is that the potentiometer feedback doesn't work, and the inlets quit working because they don't know where they're at in the controller. It's usually a broken wire or something very simple. So people get frustrated with pot defect errors, spending $30 to put a new potentiometer in and all of that. New software is available to upgrade. Slide 50. Well, let's talk about one last item of controllers that gets in the way of making barns work, and that's the problem of starting pigs in barns. See a lot of barns where the complaint is, my pens are wet when I start pigs. I need to ramp up my minimum ventilation, but if I ramp up my minimum ventilation so the pens get dry, my propane bill goes up, and you get in an endless cycle. Many times, I'd say a good share of the times, the problem isn't with the minimum ventilation in the controller. Go to slide 51. The problem is the inlets. And the reason is right here. This is the math of the inlet. Inlets work correctly when we get 800 feet per minute inlet velocity. Well, the room that was shown in slide 50 with the AP stainless inlets says that I need to set my controller at 7% of full open on stage 1 minimum to make the inlets work right. But that assumes 0 leaks into the room. Slide 52. If you look in the lower left of this one, what do we see? 52-inch fan shutter, and we can see light. Guess what? Air comes in that hole. The curtain has curtain pockets. It's maybe been hit with a power washer wand, etc. It leaks. So what do? Many times, starting pigs, rather than increasing minimum ventilation, I make fewer holes in the room by locking inlets up for the first couple weeks until pigs are going better. Slide 53. So let's end this with several examples. We said we do these advanced ventilation workshops, and what we do at these workshops is put data loggers in barns. And people tell us their controllers and everything, and then we say, how did the barn work? So we're going to look at several barns. On the upper left is a description of the barn, what the equipment is, the size of the barn, number of pigs. On the right is the conditions at the time of the logging, what the controller was, how the controller was set, what weight of pigs, etc. So here's the barn that is functioning as we would expect the barn to function. 120-pound pigs, first week in December. of 2010, somewhere in the upper Midwest, and you can see conditions are very stable. Long, steady lines means no control device is operating. We aren't changing anything. It's a very stable condition. Slide 54. However, I would recommend a few changes on this barn, and I've highlighted them in yellow. Biggest change would be 69 degrees is too warm for 120-pound pigs, and the furnace on-off temperatures are too close to the set point, risking at some point when the furnaces are going to be needed, this overshoot and a wasting of propane. Slide 55. Here's one you can see where something is working really hard to control. Up, down, up, down, up, down. Just tremendous amounts of up-down movement, especially at night in this large barn, 1,000-head wean-to-finish tunnel. Again, on the upper right are the settings. Slide 56. My recommendations on how to change these settings. So the biggest one was number 1. Stage 1 had too high of a minimum speed, so they were over-ventilating. And in fact, with the furnace shutting off within 1 degree of set point, the furnace was cycling on and off, causing the variable speed fan to ramp up, causing the furnace to come on, causing the fan to come on, and caught in an endless cycle of wasting money. Slide 57. One from just this last spring at a workshop, or just like 3 weeks ago. A nursery, again, you can see lots of movement of something trying to control temperatures in a room, causing lots of things to go on, off, on, off, on, off. Slide 58. Again, the recommended settings as to how I would set the room up in order to get a more consistent pattern of temperatures that we expect. Slide 59. One last look at another one just recently, a tunnel barn, and you can see the squiggles. Something is absolutely turning on off all the time in this barn. Slide 60. And again, a look at how I would change the settings. And again, this one is heaters because minimum speed is way too high at 75% for only 1,000 pigs in a room with 2 fans. And the furnaces were shutting off too close to set point. So we were telling the room to run the furnaces, then get rid of the heat, then run the furnace, get rid of heat, run furnace, get rid of heat. Just a constant battle that was costing the producer money. Slide 61. Final slide before we end today's talk. Here's a case of a producer who, contract grower, who was complaining about severe tail biting. And the cause of the tail biting is pretty obvious. These pigs are pissed, at the world because every day, midday, we were making the temperatures bounce around like crazy. And if you look at the settings on the controller, it's very clear why temperatures were bouncing all the time. Slide 62, how we would recommend you reset the controller to take away this bouncing temperature so that we get a steady state condition in the barn and hopefully reduce tail biting. 63, the ventilation system always does what you tell it. Absolutely. It's an absolute. Your challenge, and hopefully I've helped you understand it today, is to understand your controller well enough so that you program it so that the room does what you expect it to do as a consequence. Slide 64, the last one. Back to Mike Brumm in the University of Nebraska sweater. I do write a weekly blog. I know many of you that are listening follow it already. It's at the Minnesota Pork Board's homepage, mnpork.com, and I invite you to follow my ramblings every week about the pork industry in the United States and around the world.
All right, well, thank you, Mike, for that wonderful presentation. Again, I want to thank everybody for participating in our second PorkBridge session of this year. And with that, again, would like to thank Dr. Mike Brumm for presenting for us today. Wonderful information that we can all apply.